Hello and welcome to our presentation of our electrical engineering senior design project. We are Group 165 and our project is the hybrid drum machine. Our members are Sirokman, Kaleb McQuillan, Reid Zimmerman, and Vega Carlson. And next we'll go on to our project overview.
So as the project overview, we are making a hybrid drum machine. This is a system that allows the playback of both analog and digital drums for that can be sequenced to make a song. They will go into these parts individually as we move forward.
So the bass and tom drums utilize a bridge T oscillator to output a decaying sinusoid when they're given a 1 millisecond trigger. And there are resistive control inputs used to determine the frequency and decay rate of that sinusoid. And those are used by a combination of analog and digital potentiometers that communicate over ITC.
The snare drum is really similar to the bass drum and how the bridge T oscillator works, but it's slightly different in that at the same time, it also uses a white noise generator and mixes in noise that's similar to how a snare drum sounds when you actually hit it.
The hi-hat is similar to the snare drum in that it also uses a white noise generator that feeds into a waveform, but it doesn't use an oscillator. It just uses an envelope generator that forms a decaying exponential waveform. So that's being fed into the noise. The FM drum uses two sets of Atari Punk consoles, which are the circuit on the right, and each of those comprises of two 555 timers. There's also a bunch of potentiometers to control the frequency and duty cycle of both APCs, and one to frequency modulate the output of the first one into the second one. There's also a low pass gate that the output of the second APC feeds into that uses a Vactrol made with a photoresistor and an LED. And that creates a variable resistance that feeds into a capacitor, creating a variable RC filter. And so that helps with decaying the output slightly and also filtering out a lot of the higher frequencies.
So that is all of the analog drums. To move on to the digital drums, these are all sample-based, meaning they use pre-recorded drum samples. However, to make these more interesting, they are loaded into a programming language called Peer Data. This programming language is rather odd in that it is graphical, as you can see an example of on the right. Each drum is loaded into a sample bank, so we may select the sample per each drum and even lock them in individual steps, as you will see in a moment. These drums can also have digital effects applied to them, including filtering, sample rate reduction, reverb, and delay. It is worth noting that this is all run on the Raspberry Pi, which is also running the sequencing. However, the Raspberry Pi's built-in audio is 11-bit and PWM based, which does not sound overly great. So we added a off-the-shelf 24-bit, much higher resolution DAC to dramatically improve the sound quality. So what is a drum machine in general? There's sequencing that makes these drums play on an individual step. So if you think about this being a row of 16 steps that trigger in time, this would go da, 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 da. So we'd have these time being triggered on each one. However, that's only for one individual drum. Each drum can have a different pattern of notes applied to it, and these will stack all be mixed together so that we can get a full track out of it. Unfortunately, if we only had those 16 steps and they all looped, it would get really tedious really quickly. So we also have the ability to chain these tracks to make patterns of tracks, which can overall compose a song. So for these step sequencing, there are these 5 analog and 5 digital tracks, and each one does have 16 steps. However, we added the interesting effect of each one having 4 microsteps, which really has the functional takeaway of having 64 steps instead, making it so each track can be dramatically more interesting, have much more variation. Each of these steps can also have different parameters locked to them. What this means is that we can hold one individual step by physically holding that key on the keyboard where we enter these steps and adjust the parameter for the step. So for example, if we adjust the volume to be much louder on one step, you may get waveforms that look like this. So that does leave a question. How are we going to do that parameter locking with our digital drum or with our analog drums? To solve that problem and allow for these individually controlled steps, these volume increases or whatever other parameter, be it the decay on the bass drum, to be controlled for the analog drums, we use digipots or digitally controlled potentiometers. These are controlled over I2C and allow for us to lock these values per step. These are in addition to the analog potentiometers on the front, so that the user has both immediate live control and step sequenced in recorded control. Finally, there is pattern sequencing. So this is how those tracks can be chained together. To make this at least mildly novel, the patterns are chained in a grid. And instead of entering a pattern as like go from pattern 1 to pattern 2 or pattern 1 to 4, they are done as a sort of like Euclidean grid where you can go either move up, down, left, right, or stay in the same spot for a step. And this allows for almost generative style songs so that the repetition can even be further reduced, even though step sequencers naturally are quite repetitive. So how does this work? Essentially, the sequencer is controlled by just lots of Python code. Fortunately, this means that the programming work for this was really reduced because there are a lot of libraries that handle a lot of the work for us. For example, MIDO is a MIDI library, musical instrument digital interface, which is how we are communicating both with the control board, which Cole will cover here in a little bit, as well as libraries like psutil for detecting when peer data, the aforementioned graphical programming language is started. The drum machine state can be saved with a module called pickle, et cetera, et cetera. The one oddity introduced here is there is a keyboard library, which allows us to pick up these keyboard events for entering the step sequence. This does require root access for various reasons, which makes it so the code has to be started up on the root user of the Linux system running on the Raspberry Pi. This is unfortunate, but we deemed it an acceptable trade-off.
The two keyboards for our project are both run with QMK firmware, which is an open source firmware in C, and it enables a lot of flexibility because you can do advanced inputs like double tapping keys or working with layers. And we also can use our encoders. So it enables us to set specific functions if we turn the encoders one way or another way and pressing the encoders. So it enables a lot of versatility, which gives us a lot of options with limited number of keys.
So the controller board uses an RP2040 microcontroller. The advantages of this is that it has 6 I2C ports, which makes it easier to send out values to all of our digipots. Python is easily compatible with RP2040, which decreased our development time. So the MIDI messages that are sent from the Pi to the control board are used to sequence corresponding GPIO triggers to the drum modules, as well as values to update to the digipots over I2C.
Our enclosure was designed using OpenSCAD and a custom laser cut library that basically takes a 3D model that you make with its custom commands, and it breaks it down into a bunch of 2D puzzle pieces. So our box basically had 6 2D pieces that we laser cut, and then they had little lips in them to basically put together like a 3D puzzle. And then the power supply we used was the RT65B, has plus and minus 12 volts and 5 volts, but we turned it into 3.3 volts using a 3.3 volt regulator because the digipots had to be powered by 3.3 volts to work with the digital logic and of the I2C, and then also has a ground. And quick note, we just have to be wary because the 120 volt connections are exposed on this, so something could be done to basically add an extra layer of safety by making it so we can't come in contact with those.
The things that didn't go as planned were filtering. There was going to be 2 identical MS-20 filters that were on the output. They're just like low pass filters for, filtering out noise and other bad artifacts that we didn't really want in there, but they were soldered by hand, so they ended up being kind of finicky with getting everything working, and bad connections and things just couldn't really troubleshoot it in time. The FM drum was similar in that, it's very complex circuit. It had a lot of noise, and that caused a lot of difficulty finding where exactly the problem is because there's so many failure points because it's so complex. The keyboard LEDs, the keyboard itself was also hand wired with wire wrapping, and it got really messy really, really fast. So that made it sort of difficult because every time you bump it wrong, it would kind of disconnect. The other problem with that is that there was some bad library support, so it made it difficult to actually get the LEDs to work in the end.
So we have our analog drums to show first. Here you can hear I can change the pitch of it. I can switch between the drums that we're sequencing. So I can start by going to one of the digital tracks, and I can go ahead and enter a few steps. And when this loops back around, you'll be able to hear those triggering. So just allow me to enter a few steps. It takes a moment. So when this loops back around, I realize those two sounds aren't overly distinct, but I can switch over to a track we've just set up a little sequence here. And if I switch over to this view, you can see that when those steps with different pitch values come in, that those are showing up on the parameter display here. And I can change individual parameters. For example, I can change the sample of that drum overall. So that is on drum 7. If I go over to change, for example, just the sample, and when that loops back around one more time, I can also copy a pattern, and I can paste it onto another one. And so now you can hear that that drum is independently being sequenced. So I could copy a track into another pattern. And if I go back over into the other view here, you can see that there are 16 patterns that I can select between. Not all of these we've entered steps into, but I can also sequence those patterns themselves. This 2x4 grid down here being that pattern sequence. So I can enter like 2 right steps, a down step, a left step, an up step, a down step. And now when that pattern sequence is playing, once the end of a certain track is reached, the pattern will advance to the next one, which you can see. So as this is reaching just the end here, you'll see this dot should move down. Yes, so now move down 1 step. Again, if I go back to a step with something in it, we're back to having sound.
All right, thank you.